Software Engineering Radio Episode 51, Design by Contract.
Welcome to a new episode of Software Engineering Radio. This time it's Michael and Arno on the microphone. I'm actually going to interview Arno on Design by Contract.
Yeah, great to have you listen.
So Arno, what is Design by Contract? Where does it come from?
Design by Contract is actually a paradigm of thinking about software design. It's a way of thinking about interfaces, about the separation of interfaces and implementations. And the term design by contract is something Bertrand Meyer came up with in the 80s. He wrote the book Object-Oriented Software Construction. We'll have it in the show notes. He also came up with a programming language, Eiffel, which implements these concepts. So there are implementations that support design by contract, but the actual thing is it's a way of thinking about design. The idea is that you have abstract data types, and these abstract data types are sort of interfaces. I mean, in usual programming language, it's just interfaces that have these. And the interfaces are not just the signatures of the methods, but they also contain an implementation-independent specification of what they do. So they sort of offer a contract, which is, in a way, very natural to think about things. I mean, if we have a let's say we have a collection interface or a collection type, and we have an add method, and we have a remove method, and we have a get method, then obviously we expect the get method to return nothing in the beginning because the collection is empty, and once we add something, then the get method returns what we added before. So this goes beyond the signatures. It's sort of the meaning behind the signatures. And design by contract is a way of formalizing this. But it is a helpful mindset to have even if you do not have explicit support in the programming environment, in the programming language that you use. So
what is a contract then here exactly?
Well, a contract is actually it's a metaphor from everyday life. Contract is something we are all familiar with. The idea is that you interact with an object. You as the caller and the object as the thing that you call agree on a contract. And the object is the party that offers the contract, and you can take it or leave it, sort of. The idea is every method on the object guarantees to do something, to yield certain results, to make certain modifications, if you, as the caller, meet your part of the contract, if you meet the preconditions that the object requires. The important thing is that as in everyday life, a contract is a bidirectional thing. It's not just the object does something, and I as the caller am out of the loop, nor is it I, as the caller, need to do everything and the object can do whatever it wants. But, if I rent a room, I get the keys, I get to live in it, if I pay the rent. So it goes both ways. This is the way of thinking about it.
What is the result of a pre- and post-condition when it gets evaluated? Is it just a Boolean, or is it something more? What is the result of what can be the result of a pre- and a post-condition?
Well, as you said, pre- and post-conditions are actually Boolean expressions. Every method has a list of preconditions, which is a list of expressions that yield a Boolean. This list of preconditions must evaluate to true with the things that are used to call. And then there's a list of postconditions, also a list of Boolean expressions, and the object guarantees that if I meet the preconditions, the list of postconditions will evaluate to true after the thing was called. I think an example would be helpful here. Let's say we have a very simple method, square root, that takes a double. Obviously, the precondition, the typical precondition would be the parameter x must be greater or equal 0. Because dealing with real numbers, nothing else makes sense. And the post condition would be that the result that is returned by the method multiplied by itself is x. Well, sort of. I mean, it is never exactly x, so the post condition is formalized, so it would say the difference between the square of the result and x is less than a very small number. So you sort of give the precision with which square root guarantees to perform the calculation. And this actually shows one of the valuable sides of actually formalizing postconditions and preconditions, because it makes the precision of the operation explicit in the contract, in the signature, which is great for many applications. Most of the time you check functional postconditions, particularly like the value that's calculated conforms to certain conditions, that sort of thing. In some circumstances, there are some people doing work on non-functional postconditions, like the number of processor cycles that an operation takes, that sort of thing. But usually it's functional postconditions, functional preconditions.
On what kind of data do the pre- and post-conditions operate? I guess they operate on the parameters, they operate on the internal state, but what if the object doesn't have any state? What about a stateless object?
Yeah, excellent point. Of course, it's important to know or to specify what sort of data the pre- and post-conditions can operate on. Actually, the obvious thing is let's start with preconditions. The obvious thing is the parameters that you pass in, which I mean, with the square root example is obvious. I mean, you can always say this parameter must not be null, or that parameter must be in a range from 2, or this string must have a minimum length of such and such. So these are the typical things you often check with assertions. It's a typical thing. The code makes certain requirements on the parameters. Another set of data that the precondition is allowed to operate on is visible state, public state of the object. As we said in the beginning, design by contract is about interfaces, not about implementations. So all state that is accessible through the interface is can appear in a precondition. So, for example, let's go back to the collection example. Let's say we have a method size, which makes the number of elements in the collection part of the public interface. And then we have the, let's say, getFirst method. And let's say the contract for this collection says you're not permitted, or getFirst will return null, or well, let's make it simple. GetFirst must not be called if the collection is empty. So the precondition could be size greater than 0. This is not the only way to do it. There are good reasons for not having this precondition, but it's one possible way of specifying it, and that would mean no one is permitted to call getFirst on this collection if the collection is empty. Let's say it is a stack and you have the pop operation. It is very common not to be permitted to call pop if the collection is empty. So accessing the internal state through the public interface is permitted in writing down the preconditions. But it is not possible to reference internal state because, as I said, preconditions, postconditions are part of the interface, and the interface does not know anything and should and must be independent of the implementation. That's the idea. For the postconditions, things are a little bit more complicated. You can, again, in the postconditions, reference the parameters, as in the square root example. We said the result multiplied by itself is roughly the same as the parameter x that we passed in. You can also access the result of the operation, which is obviously necessary. And then there are things you can access the state of the object before the operation was called, and you can access the state of the object after the operation was called. Let's say in the collection example, we have a method add, which adds something to the collection. Then one of the post conditions would be the size after the operation is 1 bigger than the size at the beginning of the operation. So that is another thing that's something that is added in complexity, in possibilities for the post conditions that you do not need in preconditions.
Okay, so before we go into more detail on design by contract, what are the benefits of it?
Well, the benefit, first of all, is to specify, to have a formal specification of what code does. I mean, we all know that comments are sort of good. Many people say, write comments, comments are great. Many people say code must be commented in order to be understandable. But we also know that comments have a tendency to be outdated. Comments about what a method does are not automatically reliable. Maybe they were inaccurate to start with. Maybe some changes were made later on, and the comments did not reflect them. Design by contract is a formal way of writing down what a method does, what an interface is all about. And if you have tool support for it, we will get to that later, then during execution time, the conditions are checked. So the first and biggest benefit is pre and post conditions never get outdated. They're always up-to-date documentation about what an interface actually does, what operations on the interface do. It's something like the signature checking by the compiler. If you change the name of an operation, all the rest of the code automatically does not compile. There's an automatic check that this change needs to be reflected in all clients. Design by contract is something like that, but at the behavior level, goes deeper. But of course, there's a downside. Writing design by contract specifications, writing preconditions, postconditions is work. It does take some effort. It does take some getting used to, and the main benefit is there, at least if you want to take the effort of really being formal about it, the main effort is there if you have some sort of tool support. We'll have some common tools listed on the website, and we'll mention some of them later as well.
I could imagine that design by contract is not useful for every kind of object. Even if it has state, it might just not make sense to specify pre and post conditions, or let me put it differently, it might be impossible to specify pre and post conditions. For example, in a user interface or the like, it's hard to specify a precondition. Well, this button appeared, or this button now is pressed, or things like that. What do you think about that?
Well, interesting point. Let's take a closer look at that, because it's quite interesting. I mean, the closer you get to the borders of a system, the more difficult these sort of things get. It's the more difficult to unit test. It's more difficult to write pre and post conditions. But let's take the concrete example. Let's say we have a graphical user interface. What sort of interface would you imagine that is hard to write contracts for?
For example, when I try to visualize something, I have no means to then query my screen whether this has actually been displayed, for example.
Okay, that would be the interface to the GUI system. Sort of, you make an API call, display the button, and you have no way of actually calling an operation that tells you if the button was actually displayed.
Right.
Yes, true. There are definitely limits there, but that is a limitation of the user interface. It's an excellent point, and definitely if you use existing APIs, those usually do not come with contracts. But with the user interface, you are the one calling the interface. So the contracts are always part of the interface that is being called, and tool support must be in the component that you are calling. So yes, there are limitations there, but the limitation is basically the interface is not yours. So when the interface is not yours, you have no way of actually implementing these contracts or contract checks on the interface. But yes, that's definitely a limitation.
How does design by contract relate to inheritance? I guess it can be quite complicated. What are the rules here that I would have to obey when bringing inheritance into the play?
Yeah, again, excellent point, because inheritance is one of the really complex and weird side effect having aspects of programming with object-oriented languages. But again, it's part of the fun. The problem here is polymorphism. If you have an interface with several possible implementations, so we have one supertype and several subtypes of this, and you have a contract on the supertype, then you as the caller do not know which concrete type, which actual implementation or which subtype of this interface you are dealing with. You have a, let's say you have a list interface, which just implements a collection, then you do not know and should not know if this is just a list based on an array, or if it's a doubly linked list, or maybe even an arbitrarily huge list that is backed by a database. The idea is that you have that they're functionally equivalent. So this is the idea of abstracting the supertype out. This is what polymorphism is all about, what abstract data types are all about. And so this sort of means that subtypes must inherit all the contracts of the supertypes. I mean, if I am dealing with a list, I want to be sure that every concrete implementation of list actually conforms to the guarantees that list made. This is what makes the contracts valuable. So the basic point, the foundation of the interaction between inheritance and design by contract is subtypes inherit all preconditions and all postconditions from their supertypes. This is sort of the baseline, which is necessary for the whole concept to work. There is, however, the opportunity for a subtype to provide a better contract than the supertype. So, for example, let's stay with this collection example. I suggested that a collection has a get method, let's say a stack interface has a pop method, and this pop method in the interface, there's the precondition: you must not call pop if the stack is empty. A concrete implementation might relax this precondition and say, if you use my implementation, you are permitted to call pop. If the stack is empty, you'll just be returned 0, which is a relaxation of a precondition, which is, staying with the contract example, an improvement of the contract. I, as the one dealing with the object, I am required to do less. Another thing is the operation, or the concrete type or the subtype can provide additional postconditions. For example, the square root method in a supertype, let's say it calculates the square root with a certain accuracy. And a subtype might provide better accuracy in calculating the square root and express that in the contract. So this sort of improvement of the contracts is okay, but obviously improving the contract means that subtypes must conform to all pre- and all post-conditions of the supertype's contract. So when I'm dealing with a supertype, have reference to a supertype, and I call operations on it, I can rely on the supertype's contracts, and subtypes may provide better than that, but definitely not worse. This is actually quite important. This is one point where tool support becomes really important, because without tool support, there's actually no simple way to keep the checks synchronized. If I, for example, do things with assertions, then I have some assertions in the supertype, and the subtype needs to do the same assertions, but they need to be copy and pasted, basically. So it's very, very difficult to maintain, manually maintain design by contract in the face of inheritance.
In summary, basically, an inheriting type has to have the same precondition, possibly weaker, and the same postcondition, possibly stronger.
Exactly, yes. It demands less of the caller and can demand more of itself. This is one very difficult point of the evolution of APIs, because especially in the service-oriented architecture thing, but also in component-oriented programming in general, it is one of the tough questions is how to handle the evolution of APIs. What if an API, if an interface changes, a published interface changes, how to deal with that? If you add operations, if you want to change the name of the operation, if you want to add or remove parameters, whatever, this sort of raises the bar one further, because even if the signatures stay the same, you need the contracts can change over time, and the contracts are part of the interface. So you need to apply the interface evolution, the component interface evolution mechanisms to design by contracts as well. It's sometimes tough in practice, but it's definitely it's plain necessary. It's just the price that you pay for having published APIs. They are painful to maintain, but we all know the uses, so it's worth it. There is, however, a big benefit of having explicit design by contract annotations on the interfaces, and that is you actually see that the interface has changed even though all signatures of all operations stay the same. So if you do not have design by contract, you may not notice, but you still have the problems. If someone calls and the semantics of an operation changed, then obviously you're in trouble, and design by contract helps you to catch this sort of problem earlier on.
Next tough question. What about exceptions? I guess they cannot be easily formulated with pre and post conditions, especially not with post conditions.
You're really touching all the tough points. Great. Well, of course, exceptions that are being thrown must be part of design by contract, otherwise it just wouldn't be mature enough for practical work. Exceptions are here to stay, and they're an important, mainly the way of propagating errors in most systems. So, yes, design by contract does deal with exceptions, and basically exceptions are just a special sort of return value. I mean, they're not return in the sense of a return statement, and you have them in the as a return type, but still they are treated in the same way. So one post condition might say, if you have, if you call pop on an empty stack, this or that exception is thrown, which is a post condition. So it's one way for an operation to terminate, and that's okay. For more reference on this, I suggest you listen to the error handling episodes. They go into this also with regard to design by contract a little bit. It is, however, very, very important to keep a post condition that an exception is being thrown apart from the caller not meeting a precondition. They're very easy to mix up, and it's very, very important to keep them separated, clearly separated in your mind. If a caller does not meet a precondition, this is a bug. Always, and no discussion about that, it's a bug if a caller does not meet a precondition. Because that's what preconditions are about. Bertrand Meyer once said, if you use design by contract and a caller does not meet a precondition, it's okay for the system to crash, basically. Crash in a graceful way that helps debugging, that sort of thing. But preconditions are not for not to be caught later on. So, oh, I didn't meet the preconditions, so I'll deal with that and try something else. Preconditions are hard. They are a hard barrier that you have to pass through. However, if it's very different for a postcondition that says if under these and that circumstances an exception is thrown. Because that is sort of valid behavior. You met all the preconditions as a caller, and the code that you call decided, or well, it laid its card on the table, sort of saying, if these and that conditions are there, then obviously I will throw this or that exception, which is then catchable, and you can base decisions in the calling code on these exceptions, anything at all. But it's a very, very important distinction between these two.
Okay, so when you say it's a bug, then this leads instantly my thoughts to the idea that design by contract is mostly useful at development time, when I didn't ship my system. When I ship my system to my customer and I have the tool or the technique of design by contract still enabled, is it a good or a bad thing that the system crashes?
Oh, very, very, very good question, actually. I would say this is something similar to having assertions turned on or off in production. There are some contexts where it is desirable to leave them on. For many business applications, for example, I would say it's a good idea to keep them on because, well, there is, or if a precondition is not met, the behavior of the system is sort of undefined, and you usually want to avoid that. So, and obviously, this is not about crashing the system. In real systems, there's often a more robust way of handling this, but still, sort of a hard abort of this thread and notification to the thread scheduler, whatever, that this operation really, really failed, that sort of thing. And I think, yeah, that is quite helpful, even during production, because, you really find your bugs. That's the idea of it. There are, however, applications, let's say a pacemaker in a heart, or the flight control software for the space shuttle. So this sort of life-critical, mission-critical software, where it is better to go on with inconsistent state than failing the process altogether. I think it's a trade-off, but I would tend to leave them on in many systems.
Okay, most languages do not support design by contract directly, so what chances do I have to use design by contract as a means for development?
First of all, first opportunity to use them is switch to Eiffel. No, just joking. Eiffel as a language has the support, and it's a great language to look at if you want to understand the concept. But of course, this is not a really practical approach because you don't do your projects in Eiffel usually. There are constraints on that. There are good reasons not to use it. Well, the first thing you can do is actually just write the comments in a more or less formalized way. Design by contract is a very valuable tool even if you just have the mindset. If you think about your interfaces not only in terms of the signatures of the operations but also in what do these operations do? What requirements do they pose on the caller, and what guarantees do they provide when they are being called? This is sort of the first step, getting into the mindset. Another step you can go beyond that is there are tools for quite a lot of mainstream languages, for C, C++, for Java, I think for Ruby as well. Probably for basically all of the mainstream languages now, but those are the languages of which I heard of the tools or have seen them. And they are, well, the C++ approach is based on macros usually, macro expansion. In Java it is Java doc comments that are processed by a preprocessor, and so the code is instrumented. There are tools that you can actually use, and yeah, it's a great way of doing this. Of course, this has some influence on your on your development environment, on your build process, and this sort of thing. But that's definitely a way that you can go. But if you don't want to go that effort, or add another tool, another library, you can always start with using assertions. So that is very, very limited in scope.
So design by contract seems to be similar to the assertions. Where's the difference? Where's the limit?
The thing where they go close together is you have conditions that are checked at runtime, and these conditions that are checked at runtime sort of abort the thread in a way that is not intended to be handled, saying this is a bug. Preconditions are actually quite easy to implement using design by contract. You can have assertions at the beginning of an operation, checking for parameter validity, calling or comparing, or checking some constraints on the size. If you have a pop operation for a stack, it's easy to have an assertion that says size must be greater than 0. So preconditions are quite easy to implement using assertions, although you do not have inheritance. If you have a super type, you cannot specify assertions in an interface, in an abstract type. You can only have them in the implementation, and you have no support for propagating them, for checking that the subtypes have the same contracts as the supertypes. The thing becomes even more difficult for postconditions, and the reason for that is that postconditions oftentimes compare the state of the object at the beginning of the operation to the state of the object at the end of the operation. And having that sort of thing requires the use of temporary local variables that are initialized in the beginning and then read at the end of the operation. This is very, very hard to maintain manually. You can do this, but technically, of course you can do it. I mean, the programming language that you use is capable of it, but it's very, very hard to maintain. It's not very practical. So basically, checking postconditions is where assertions fail, where assertions are not enough, or where the big benefit of having a tool for design by contract compared to assertions is.
We just learned that I can improve the quality of my software using pre- and post-conditions. So is it valid to say, well, using pre- and post-conditions, I save all the automated testing?
Well, there are some people who say that actually, but I wouldn't agree. I think they go very well together, because the scope and the time when they are run is different. Pre- and post-conditions are checked at runtime, whereas unit tests of the whatever unit family type, they are checked at build time. So you often you have a desire to find your bugs during build time as early as possible, or as many bugs as possible before the system goes into manual testing or into production. But if you have pre- and post conditions, this makes the writing of unit tests simpler. You sort of just call your operations, go through the business code, and the pre- and post conditions do much of the assertion checking that you would otherwise have in your unit tests. But they're not a replacement for all the assertion checking that the unit tests have. And of course, you have to write the fixtures and be clever about some things, writing the tests still. So they're complementary. They go together quite well.
This kind of closes our episode. Would you mind summing up what we just learned as a closing?
Sure. Design by contract is a way of thinking about interfaces, about abstract types, and thinking about them not only in terms of operations and their signatures, but also in terms of the semantics behind those operations. That is, it's not only the name of the operation and the names and types of the parameters and the return type, but also under what circumstances does this operation do what, and what do I as a caller have to do for this operation to do what it promises to do. This is the key thing about design by contract, and if that's the only thing you remember from this episode, that's great. But you get additional benefit if you have tool support for this. There are ways of writing formalized conditions as annotations to the operations, depending on the tool, depending on the programming language, and then these are checked at runtime. And this is obviously additional benefit. And these tools also ensure that contracts are maintained in inheritance hierarchies. They ensure that every subtype offers at least as good a contract as the supertype does. So these are additional benefits you get if you use tools, but even if you just keep this mindset of an operation is more than just a signature, it is a contract, it is a list of guarantees that I as a caller have to provide, and then the object guarantees to do certain other things. And this is not part of the implementation, but it is part of the interface. This way of thinking about interfaces, about interface operations in terms of contracts, is really valuable even if you don't use tools.
Great. Thank you, Arno, for explaining design by contract to us.
Thank you, Michael. And thanks everybody for listening. Hear you next week.
Bye-bye.
Bye.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.